Welcome back to the next video, everybody. I'm back with a vengeance. I have a new iPad. I have a new Apple Pencil. Let's go. Today's video topic is the dual Hopf algebra and Cartier duality. So first of all, we'll talk about the dual functor. We'll let R be a ring. We'll take an R module M and we'll denote its usual dual by M prime. So that's all the R module maps from M to R. And we'll denote by bracket M prime M the quantity M prime of M. If M prime is in big M prime and little m is in big M. If M and N are locally free of finite rank, you've got these natural homomorphisms, and I'll let you find them from M to the dual of the dual, M prime prime, and from M tensor N prime to M tensor N all prime. And these maps are isomorphisms. And so the upshot of all this is that the map that sends M to M prime is a contravariant equivalence of categories from the category of R modules to itself, and that this functor commutes with tensor products. Fantastic. All right, let's specify to R setup. From this, we see that if G is spec A is a finite flat R group scheme, the thing we care about this chapter, then the dual A prime of the commutative Hopf algebra A is a co-commutative Hopf algebra. And what should happen there? Well, the multiplication A prime tensor A prime to A prime should be the dual to co-multiplication M tilde from A to A tensor A and vice versa, as expected. The unit element in A prime should be the co-unit epsilon tilde from A to R and A and vice versa. And then similarly, the antipodes are dual to each other. So all of the stuff we expect to happen. Reversing arrows, okay. How about the case where we're dealing with a constant group scheme over a finite group? So if G equals H sub R is the constant R group scheme associated with a finite group H, then A in this case will just be the ring of R valued functions on H. We already knew that. And so what's A prime? It's R kind of adjoin H. It's the group algebra of H over R. So it's like formal linear combinations of stuff in H over R. And the pairing here is what? It's bracket sum over x and h, r sub x, x, comma, f. And what should that be? Well, it's the only thing it really could be. It's the sum over x and h of r sub x times f of x. Okay. How about the general case? So in general, you should think of A and A prime roughly as analogs of the ring of functions on G, the group scheme, and the group algebra of G, respectively. Now, this isn't quite right. It's mostly right. So the first part is definitely right. If f is an A, then f does give a b-valued function f sub b on G of b, the b-valued points of G, for each R algebra G. And what is that function? You just set f sub b of x to be x of f for each point x. And what is x here? It's an element of G of b, right? So it should be a map from A to B by equivalence of categories, if you like. But the analogy, at least for this first half here, is even stronger than that. Not only does each f and a give rise to a b-valued function f sub b on G of b for each b, but f is determined by these functions. In fact, something better is true, though. F is even just determined by f sub a, because f is just f sub a of ID, where ID is the identity map in G of a, and where G of a is shorthand for G of G, of course. Okay. Now, the analogy breaks down a little bit when you move to A prime. A prime is not actually the group algebra of G, or of G of R, rather, but you can check that there's there's an inclusion G of R, which is by definition / by equivalence of categories, R algebra maps from A to R. That, of course, lives in our module maps from A to R, and that's A prime, okay? So what is G of R as it sits inside A prime here? You can identify G of R with the multiplicative group of group-like elements, which we talked about several videos ago, of A prime. That is, it's the group of invertible elements lambda and A prime, such that lambda maps to lambda tensor lambda via co-multiplication in A prime. Okay, so it's kind of the group-like elements in A prime, rather than just like the entirety of A prime or what have you. Okay, the last thing I want to say for today is, does this whole concept play nice with base extension? Yeah, formation of the dual Hopf algebra A prime does commute with base extension. What I mean by that is, for each R algebra B, we can identify A prime tensor over R B with A tensor B over R all prime, as we talked about on the first slide today. And the second dual here, of course, is with respect to base B. And so G of B is the group of group-like elements in the Hopf algebra A prime sub B, which by definition is just A prime tensor B over R. And this holds for every B, where B is any R algebra you like, okay? So everything works like you think it does. Essentially what I'm saying is the formation of the dual Hopf algebra commutes with base extension. In this case, we'll denote the B bilinear pairing from A prime sub B across A sub B to B by just bracket sub B, basically. What I mean by that is for each f and a, or A sub B, and x in G of B, which we know is an A prime sub B, the value of f at x should just be f sub B of x, which by definition is bracket x comma f sub B, which is in B. And in particular, if you take f in A and just the identity element in G of A, which you can think of as living in A prime tensor A, we have that f is f sub A at identity, which using our bracket notation is bracket identity, comma, f tensor 1 sub A. So this is just kind of a lot of details to make sure everything works. Does the formation of the dual algebra actually commute with base extension? How do functions work? How does the bracket work? How does the bracket extend? Does it work in the same way as when we are working over the base ring, etc.? All right. And so I will catch you guys tomorrow for the next video, and thanks for watching.